Hello students, today we are going to start a new topic, kinetic theory of gases. Let me first understand the molecular nature of matter. You know that matter is made up of atoms. According to John Dalton. According to John Dalton, a scientist, there are two laws of formation of matter, out of which the first law is any given compound of its constituent mass. Whereas the second law states when two elements form one compound, the ratio of mass of constituents element are in a ratio of small integers. According to first law, suppose a compound is formed in such a manner that the element by which the compound is formed has atom to form a compound, and all the constituents atoms are the same, or you can say are from same element. Whereas in the first law, the scientist says that the two different elements are forming a compound where the ratio of different elementary masses are in a ratio of small integers. Also, there are some other theories by another scientists, in which first is Gay-Lussac law, that is, when the different gases combines to yield another gas, their individual volumes are in the ratio of small integers. Another hypothesis given by Avogadro is equal volume of gases, equal volume of different gases have same number of molecules at equal temperature and pressure. Means if the two gases have the same temperature, have the same pressure and the same volume, in that case the number of molecules in their particular volume will be the same. That is Avogadro hypothesis. So we have discussed the general and basic hypothesis and the laws provided by the various scientists regarding various cases. Now we will take how the gases behave, behavior of gases. Gases at low pressure and high temperature satisfy a simple relation such that PV equals to KT, where P denotes the pressure of gas, V denotes the volume of gas, and T denotes the temperature of gas. And also there is a constant which is K, and this is the constant for the given sample of gas which is proportional to the number of molecules present in that volume of gas. So it is a constant which is proportional to number of molecules present in the volume of gas sample. So here it is given by K is given by n small k, and n equals to number of n equals to total number of molecule in gas sample, and the small k is known as Boltzmann constant. And its value is given by 1.38 multiply 1.38 multiply 10 to the power minus 23 joule per Kelvin. So in the equation PV equals to KT, the constant K depends on the total number of molecules present in the gas sample, which is N, capital N, and the small k, the Boltzmann constant, which is same for all types of gases. The value of K is same for all gases. Thus, if we have the two different gases at different pressure, temperature and volume with the different number of molecules in their sample volumes, then the value of K, the Boltzmann constant, will be same for all. Then we can write it. Consider for the two gases samples of volume V1 and V2 with their respective pressure and temperature, P1, T1 and P2, T2 and number of molecules in their samples as N1 and N2. We can say that P1V1 equals to capital K T1 or N1 small k T1. This for the first case, and for second case P2V2 equals to the constant K dash and T2, which will be equals to N2 K T2. In both of the equations, the parameters pressure, volume, temperature and the number of molecules in the sample volume are different. But the value of Boltzmann constant, which we are considering here as the K notion, is the same. So by comparing both of these two equations, we get P1V1 upon T1 N1 will be equals to P2V2 upon T2 N2 will be equals to small k, which is the Boltzmann constant. Throughout this chapter, we will use the notion of Boltzmann constant as k as a subscript b, k and its subscript b instead of small k. We are doing this for just our simplicity so that we can remember this constant in terms of kV. From the above relation, P1V1 upon T1N1 and P2V2 upon T2N2 equivalent to Boltzmann constant, we can properly understand that whenever the pressure, temperature and volume of the two different gases will be the same, then the number of molecules in their individual sample volumes will also be equal. That will be equal. So there is another Avogadro hypothesis. If both gas samples has same pressure, temperature and volume, then from the above equation we will get 1 upon N1 equals to 1 upon N2 equals to Kb, the Boltzmann constant. And from this relation we can get it here N1 equals to N2 equals to 1 upon Kb, that will be equals to 1 divided by 1.38 multiply 10 to the power minus 23. The value will be equivalent to, so we can see here that according to Avogadro hypothesis, in 22.4 liters of any gas sample, at a fixed temperature and pressure, the number of molecules Na will be equals to 6.023 multiplied 10 to the power 23 molecules, which is known as Avogadro number. The mass of molecules Na for a gas, volume of 22.4 liter at standard temperature and pressure is equals to molecular weight of gas in grams, and this amount of substance is called 1 mole. So that's all for today. We will meet in the next topic. Till then, good day.